Hello, this is Ana Doblas and this is the first video of the module Beam Optics of ECE 513 Intro to Optics and Photonics. The learning objective of this class is knowing a little more about the features of a Gaussian beam, being able to identify and define the Q parameter, and from the Q parameter knowing in which position we are from the Gaussian beam, which is our observation plane and what is the Rayleigh range. And we're gonna be able to define the radius of curvature and the beam width from the Gaussian beam. And we're gonna use this as our independent variables to estimate the observation plane and the beam width of the Gaussian beam. And finally, we're gonna introduce the complex amplitude distribution and its radial distribution of a Gaussian beam. So let's talk about a little more about what a Gaussian beam is. So we know that its beam power is principally concentrated in a small cylinder around the optical axis. So I like to kind of represent the Gaussian beam like a Gaussian function. Oops, sorry about that. Let me try to do a better job, like a Gaussian function. And we know that within the center, that's where we concentrate the all amount of the power, and it's always around the 86%. So let's say that we are propagating a Gaussian beam. So something that is really important is that the intensity distribution, and that's something that we're gonna see in the next, it's always gonna follow a Gaussian beam. So we always gonna change the width. It's always gonna get more spread out, but we're always gonna have the same amount of power around the center. So when we define through the Gaussian beam, we're gonna talk about, so this is our optical axis. So this is gonna be our Gaussian width that we're gonna define as the WC. And we're always gonna have a minimum here, which is gonna be defined by our Gaussian waves, and it always gonna increase when it propagates. So we're gonna, around the Gaussian waves, we're gonna define a region where roughly the beam is not gonna change a lot. So this is gonna be double of our Rayleigh range, and this is where we're gonna consider that the Gaussian beam is a plane wave. And when we are really far away for values of the distance that is really far away for the Rayleigh range, then our Gaussian is gonna become a spherical wavefront or a spherical beam. So that's where it's gonna be important. So thinking about Gaussian beams, we need to think about Gaussian beam as a paraboloidal wave. So this is the expression of our paraboloidal wave that we have given in the previous module, in module number 2. But now the main difference is that every time that we define the distance c, we're gonna think that our paraboloidal wave has been shifted. So instead of having c, we're gonna keep a general definition that is q, which is a shifted paraboloidal wave where now the center is an epsilon instead of c equal to 0. So that's kind of like the basic idea. We just think about a Gaussian being as a shifted paraboloidal wave, but now we're gonna go a little a step forward, and now our q value, which originally was c minus epsilon, we're gonna allow that epsilon is gonna be a complex number, and that's where we define our q number. So q number is gonna be c plus j c sub 0, where c is gonna be the distance of our Gaussian beam to the beam waves, and c sub 0 is gonna be the Rayleigh range. So what is exactly the Rayleigh range? So this is how we have here a representation of the Gaussian width. So this is gonna be our Gaussian width, and we see that it always increases with the value of c, except when we have a minimum value that is W sub 0, so that's gonna be my beam waist. So we're gonna define the value of the range, the Rayleigh range is such a position where the beam width increases by square root of 2. So that is particularly where we are gonna define how we define the Rayleigh range. Is the value of the actual distance where the beam width of the Gaussian beam increases by square root of 2 the beam waist. So let's do a really simple in-class problem. So we have a Gaussian beam and we know the Q parameter, we know that is 3 plus J4 centimeters, and we need to find the observation plane given from the Gauss beam waist and its Rayleigh range. Alright, so I'm just gonna go ahead and solve it. So if you remember, the Q was defined by a complex number when we were having C plus J, and then the other part was the Rayleigh range. So it was a complex number, right? So now the Q given by the problem is the real part is 3 and the complex number is 4. And all of this is on units, centimeters. So just making direct observing the both equations, we can identify that the position of the Gaussian beam with respect to the beam waist is 3 centimeters, and then the Rayleigh range is 4 centimeters. So somehow, based on that problem, that means that we are somehow here, right? This is gonna be 3 when the Rayleigh range is 4 centimeters. So that's really super simple problem. So let's talk. So alright, so we know that the Q parameter is a complex value where the real part is telling us the distance of the Gaussian beam to the beam waist, and then we know that the imaginary part is telling us the Rayleigh range. So we can do the inverse of the Q parameter, and we work a little to the map, so we know that the real part of the inverse is gonna be related with the beam curvature. So if we kind of write the beam curvature, that's gonna be C squared plus C sub 0 squared C, and now we can have this as C plus C sub 0 squared over C, and I can take a C outside, and that's gonna be 1 plus C sub 0 over C squared. So that's gonna be my equation for the beam curvature. And now when we have the beam width, we know that pi the square of the beam width over the wavelength, that's gonna be C squared plus C sub 0 squared over C sub 0. And now I can work a little more the right side of the equation to kind of put it similar to what it was on the beam curvature. And now the beam width square, I'm just putting here the other, so we're gonna have lambda C sub 0 over pi, and then 1 plus C over C sub 0 squared. And here, if we introduce, and I'm introducing this a little early, but if we introduce the beam waist as expression of the Rayleigh range, this is gonna be the square of your beam waist 1 plus c over c sub 0 square. So this is how we can define the beam curvature and the beam width. And here we have both equations where I just introduced to you what is the value of the beam waist. So let's do the next problem, which is, excuse me, they want us to estimate the position C and the beam waist, assuming that we know the beam width and we know the radius of curvature. So how we're gonna work this problem. So it's gonna be a little long, so hang with me a little bit. So my first equation that we have is the one of the radius of the curvature, c 1 plus c square over c square, and I can write this down as c square plus c sub 0 over c. And if I write it down in that way, the c that is on the denominator on the right equation, I can move it to the left as a product, so then we're gonna have c squared plus c sub 0 square. The second equation that we have is the one of the beam width. Which here is the beam waist, the square root of 1 plus c squared over c sub 0 square. And now if we make the square of all of them, the beam waist is gonna be the beam width square, it's equal to the beam waist square. And then we have here, I'm just gonna say the Rayleigh range square c square over the Rayleigh range square. And instead of having the beam width, we can write this as the beam waist square as lambda c sub 0 over pi. So we have here that the beam width is equal to lambda c sub 0 over pi c sub 0 plus c square over the square of the Rayleigh range. And now these cannot cancel each other, so we have lambda over pi c sub 0, c is the square of the Rayleigh range and the square of the distance. And I want you to pay attention on this part because these two are the same. So I can write this part combining with the equation number 1 as the curvature multiplied by the distance. So now what we have is, sorry, I didn't mean to change the color. What we have is the square of the beam width is equal to lambda pi the Rayleigh range, and then we have the radius of the curvature multiply with the distance. So I can write at the end, and I'm just gonna use another color, and we can write the Rayleigh range as lambda c the radius of curvature over pi the square of the beam width. So we have here the Rayleigh range in terms of c, the beam width, and the radius of curvature. And this is not what the problem is asking us. The problem is asking us to know the value of c, so we need to go a couple of steps further, but moving forward, this is gonna be my equation number 3. So now what I'm gonna do is I'm gonna replace equation number 3 in equation number 1. So you remember number 1. Number 1 is the one that says that the product of the radius curvature with the distance, this is c squared plus the square of the Rayleigh range. So now here is, that's where I'm gonna introduce equation number 3, because I know that the Rayleigh range is lambda squared c squared over pi squared, the power of 4 of the beam curvature, and then the square of the Rayleigh range. So here what we're gonna have is my radius, and I'm kind of multiplying everything. I'm removing a c across, so we have c plus lambda c radius square over pi 4 omega 4. So we can take out, and I'm just gonna use now a different column. We are taking out the c value, so we have 1 plus lambda square radius square over pi. This is number 2. Oops. This is a number 2 here. So omega square. So this is like c pi square power 4 of the beam width lambda square radius square pi square p square. So now my distance is gonna be as the radius by now my width, and then pi power 4 of my width plus lambda square and the square of the radius of curvature. So this is one of the outcomes, which is the location of Gaussian beam. In terms of the radius of curvature and the beam width, which is exactly what they were asking us. So now we go back to our equation number 3, because they are also asking us our beam weight. So we have here that the Rayleigh range is lambda by the square of the beam width, and now here we have our distance theta, and then we have our radius of curvature, right? So I'm gonna kind of place now our new equation before, like when we were getting, so that's gonna be the radius of the curvature pi square 4 and we have here our radius of curvature. So this is at the end, we can see here that this can go with one of these, and here we have now a 2. So my Rayleigh range is equal to lambda the square, and now we have pi and the square of the beam width, and then the denominator stays exactly the same. So this equation right here is the Rayleigh range in terms of the radius of curvature and the Gaussian beam. And now finally, if we know the Rayleigh range, we definitely can get the beam waste, so it's just kind of placing lambda over pi, like lambda r reduces pi so here, like pi, they cancel each other, so well, all the thing of the denominator is gonna be a square, so with the square root it's gonna cancel out. Now on the denominator we have to do the square root of pi square, the power of 4 of the beam width, plus lambda square and the square of the radius of curvature. And this is how we have the beam waste in terms of the beam width and the radius of curvature. Just to finalize this video, so remember that we were saying that a Gaussian beam is just a shifted paraboloidal, so that's gonna be our complex amplitude distribution, where all this part is the amplitude information, and we see that it changed with the beam width, and it also is gonna change along the XY axis. And then here is where we have our phase that is gonna change how it propagates. This is our paraboloidal factor with the radius of curvature. We have a phase retardation that we're gonna talk in the next class depending on the Rayleigh range, and here we have our plane wave propagation. Something that is important to notice is that we need 4 independent variables to define a Gaussian beam, and when we know the complex amplitude distribution, always we can get the irradiance distribution as the square root, as the square of the absolute modulus of the complex amplitude distribution. And here is when we only have how it changes the intensity along the XY axis, but it changes with the value of C. This is what I have for your class number 10, the first class in Gaussian beams. Thank you.